Today's topic is physical significance of the third law. Before determination of the physical significance of the third law, we should must know how the equation is derived. You have derived it in the previous lecture for the topic of the third law, so I am just revising it for you. As you know that the molar heat capacity is equal to the heat divided by time at constant pressure. When we put the value of the heat, that is TDS. So when we arrange the equation for to determine or to take out the value of the entropy, so the numerator on the right side become denominator on the left side, and the equation become in this way. And when we apply the integration on the right and left side of this equation will appear in this form, where here the S0 is the entropy, is the limit of the entropy when the temperature is 0, and the ST is the limit of the entropy when the temperature is available and temperature is present. So for the here is also the limit for the molar heat capacity for the 0 temperature and the for absolute temperature and for somewhat temperature. When one opens up or apply the entropy limitations, then it appears in the form St minus S naught, that is entropy at temperature and entropy at the 0 temperature, and this is the right hand side. According to the equation for finite value of this St minus S naught, Cp must be absolute 0. Hence third law can be stated like this, because we have said it earlier in the third law of thermodynamics and in the second law as well, where we said that the entropy of the system at absolute 0 temperature become the 0. So we are taking the left hand side equation that is about the entropy as 0. Only the factor that is to be studied is the molar heat capacity, that is when the limit is applied temperature approaches towards 0, that also become equal to 0 for the crystalline solid form. Keep it remember or keep in your mind this specific equation that we are going to use further for the determination of the physical significance of the third law of thermodynamics. Determination of the absolute entropy of a substance. This is the physical significance of the third law, that we can determine the absolute entropy of a substance. How we can determine the absolute entropy of a substance? For this we will take the use of this equation. First of all, we will say that when we know already that the entropy of a system at the absolute 0 temperature is 0, so we will neglect this entropy and only the equation remaining is this. Here the St is the absolute entropy of a substance at some temperature, at temperature T. So it means that at that temperature T, the entropy obtained will be specified entropy or the absolute entropy. And when we determine this law about the integration, where we know already that and have applied this law variously, where we said that differential of the natural log temperature divided by differential temperature is equal to 1 over T. It means that this dt that is in the denominator can become numerator on the right side, and the equation become in this way. So finally, here in this equation where dt over T is given, we can put in place of dt over T, mean differential of temperature divided by temperature, can be replaced by the differential of natural log T. So when we put the value of the dt over T, that is d natural log T, in the equation become in this form. When we remove this natural log in the place of the general log, that is 2.303 log. So 2.303 is a numerical value, constant value that will come out of the integration, and the natural log is replaced by this general log. Okay, now next, after this derivation that we have obtained here, this is the experimental evidence of third law of thermodynamics. The value of the above definite integral can be obtained by measuring the area under a curve of Cp and log T. What is that definite integral? Definite integral is actually the absolute entropy that we are supposed to determine, and it can be determined by drawing a graph between the molar heat capacity and the log T. The area that is obtaining here in the dotted line is about the measurement of the absolute entropy. The total absolute entropy of a system in a particular state at a given temperature will be the sum of all the entropies of all the stages from where a substance has to go through. Means that if we are talking about the entropy of the gas, we must know the entropy of the system at the solid state. Then when the temperature is higher and the entropy is increased from the solid state to liquid state, what was the entropy at the solid liquid state? When then we will convert this liquid into the gas form, it means that we will increase the temperature, so entropy change from liquid into the gas. And when we measure the entropy of the gas, it must be the sum of all the kinds of entropies, mean entropy of this at the solid state, entropy at the liquid state, and then entropy of the gaseous state. It means that when we talk about a certain specific state of entropy of a substance, it must be the sum of all the previous stages entropies of a system that it has to undergo in order to reach that particular state that we are studying. From the crystalline state at zero means that we will take the material from the 0 Kelvin, from the crystalline form, then into the further next stage, into the next stage, and finally into the gaseous state. The entropy of a gas must be equal to the sum of all the entropies. And here in this graph it is showing that when we use the molar heat capacity against the log T to make a graph, then we get this graph, and here in this graph the area is showing to the specific or absolute entropy. Let's study how the previous equation can be used to determine the entropy in the sum up way after adding all the entropy of all the stages. The number one thing is that if the state of the material is solid, as we are talking about the crystalline form of the state, that is solid state, when heat is provided, temperature is increasing from the 0 to the point of the temperature where it start to melt. Then this change of the substance from the solid to liquid is called the melting point, and the entropy change will be the entropy of fusion. Then heat the liquid obtained, it is further heated, or it more heat is applied, then that liquid will start to be converted into the gaseous form, or gas start to be boiling up and start getting converted into the vapor phase. So that temperature will be called as the boiling point. And the heat of and the entropy at that point must be the entropy of vaporization here, because the component or the system is changing into the vapor form, so that entropy is the entropy of vaporization. Then entropy of heating the gas, that is the entropy of heating the gas, that is somewhat about the gas is being heated further, even it is converted into the gaseous form up to the 25 degrees Celsius or 298 K. The absolute entropy of a gaseous substance as a temperature T is given by this equation. How this equation is useful to determine the various forms of the material entropy? This is the equation for the determination of the absolute entropy for the different material. For example, this is the same equation, but the equation is extended form. For example, you have got this equation in the previous, just a latent heat of fusion is added, and then temperature range is changing. Okay, this is a part of the equation that is for the substance when it is getting converted from the solid form into the liquid form, because the temperature is increasing from the 0 to the melting point. So this equation portion is useful for the solid form, plus latent heat of fusion is given. It means that the substance is getting converted from the solid into the liquid and the entropy of the fusion is obtained. That this portion is added, that is the latent heat of fusion. Then next is the same equation is repeated for the material substance when it is in the liquid form and it is getting converted into the gaseous form by giving the boiling temperature, and this is the heat of the vaporization that is added in the same equation. Next portion is for the gaseous state, when the state is of the material is already in the gaseous state, further heat is applied and no heat of the and no other latent formula is added because it is already in the gaseous state. If a substance is in the solid form, then only this portion of the equation is applicable, and if the substance is in the liquid form, then you must know that liquid is gained from the solid stage, means that the liquid has to pass from the solid state. It means that its entropy must be equal to the entropy of the solid state plus entropy of the liquid. So both of these portion of the equation are useful. And when we talk about the substance in the gaseous state, then it means that the gaseous state is obtained by passing from the two more stages, that one is from the 0 to to the Tm, mean from the zero temperature to the melting point, from the Tm to the Tb, mean from the melting point to the boiling point, and then from the boiling point the temperature is further increased of the gas. It means that in case of the gas, all of this equation is useful, all of this equation will be used. The third law is not actually the law because it is not experimentally observed and experimentally performed, but this law gives the conclusions that are very realistic and that are very near to the agreement of the experiments that are to be performed. Means that it is not experimentally proved law, but the conclusions obtained by using its theory or its hypothesis is really close to the results obtained, so it can be regarded as a law. This was all about your third law of thermodynamics, and that was all about. And if you, in case of any query, any question, any problem, you can ask. Thank you.